In an earlier lecture, we discussed how to compute the dipole electric field at an observation location O by superposing the fields computed for each of the two source point charges which are of opposite sign, have the same magnitude of charge, q greater than 0, and are separated by a distance s. We found one way to express the E field of the dipole as follows, where the vectors r plus and r minus are, respectively, the relative position vectors that point to the location O from the point charges plus q and minus q, respectively. We also talked about the vector dipole moment P, which has a magnitude equal to the product q times s, and a unit vector, p hat, which is a vector of length 1 that points from the negative charge to the positive charge. Recall, too, that we were able to express the vectors r plus and r minus in terms of s, p hat, and the position vector r that points from the center of the dipole to the observation location. Finally, you will remember that we use these expressions to consider a special case where the observation points lie on the dipole axis. Today we're going to consider another special set of observation locations that are equidistant from the charges and lie on a plane that is perpendicular to p hat, and the plane bisects the line segment that joins the two charges. That is, this plane of observation points passes through the center of the dipole. Let's start by looking at observation point O, which lies on this special plane as shown in the figure. Notice that for this special case, the vector magnitudes for r plus and r minus are equal. Additionally, each of these magnitudes is the length of the hypotenuse of a right triangle whose legs have length s over 2 and the magnitude of the vector r, respectively. This means we can write the magnitudes of r plus and r minus as follows. Also, from the geometry of the same triangle, we can find the cosine of the angle theta shown in the figure. We will use these expressions in a moment. First, let's use our results for the magnitudes of vectors r plus and r minus to rewrite the expression for the E field for a point on this perpendicular plane. Let's now calculate the vector subtraction of the unit vectors r hat plus minus r hat minus. Looking at the sketch shown, we see that the resulting subtraction leads to a vector whose direction is given by minus p hat. That is, points in the direction opposite to the direction of the vector dipole moment. And with a little trigonometry, we can see that the magnitude of this vector subtraction is given as shown. Now, we can use our earlier result for cosine theta to write the difference in these unit vectors as follows. And therefore, our expression for the dipole electric field on the perpendicular plane becomes as shown, where we use the fact that the magnitude of the vector dipole moment is the product q times s. Notice that the dipole E field on this plane always points in the direction opposite to the direction of the vector dipole moment p. Now let's consider observation points at distances r, which are large compared to the charge separation s. In that limit, to a good approximation, we can then ignore the terms involving s in the denominator and obtain this result. Now, it's interesting to look at the magnitude of the E field in this plane for the magnitude of the vector r much larger than s. Now, if we compare this expression with a very similar expression we found for the magnitude of the E field for on-axis observation locations, then we notice two things. First, we see that at the same large distance from the dipole, the E field on axis is twice as large as the E field on the perpendicular plane. Second, we see that far from the dipole, the E field in both cases varies as the inverse cube of the distance. In fact, this dependence is not limited to these special observation locations. It can be shown that this dependence applies for all observation locations that are far from the dipole. Let's try to answer the following questions using the ideas we just discussed here. What is the direction of the electric field at the location C due to the dipole? The answer is number 4. Notice that the observation location is located on the perpendicular plane. As we discussed earlier in this lecture, the direction of the E field at locations on this plane are opposite to the direction of the dipole moment. Since in this problem, the vector dipole moment points in the direction 8, that is, from the negative charge to the positive charge as always, that means the opposite direction is direction 4. Now let's try this question. What is the direction of the net electric field at location A? Here's a hint. We have 2 dipoles in this problem, so to find the answer, we will need to apply the superposition principle to find the total electric field due to both dipoles at the indicated observation location. The answer is number 3. Here's how we arrive at this. First, we notice that both dipoles have the same separation S and charge magnitude Q. Second, this observation location lies on the axis of one of the dipoles. The E field due to this dipole points to the right. Third, that same observation location lies on the perpendicular plane for the other dipole. For this situation, the E field due to that second dipole points to the left. Now, since the location is the same large distance from both dipoles, that means the magnitude of the E field for the first dipole is twice as large as the magnitude of the E field for the second dipole. Thus, that means the net electric field due to both dipoles give a result which will point in the same direction as the larger on-axis E field, that is, in the direction to the right, which is direction 3.